Welcome to the deep dive. We take complex stuff, boil it down, and give you the key takeaways.
That's the idea.
Today, we're jumping into a really interesting paper from IE Access. It's all about controlling microgrids, those smaller, local power grids. Our mission, to really unpack how they're managed, especially this thing called the secondary control layer.
And crucially, the communication challenges involved there. It's more complex than you might think.
Exactly. It's the shortcut to understanding where energy is heading, and it really does get fascinating.
Okay.
So let's unpack this. Microgrids are, well, they're a pretty big deal now.
Definitely. They let us weave in things like solar, wind, storage right into the local grid. Makes it more robust.
Right, adds resilience.
Yeah.
But getting them to work smoothly, efficiently, that needs some smart control.
Sophisticated control, absolutely. And this paper talks about a layered system, a hierarchical control, 3 layers working together.
3 layers, okay.
Yeah, and it's neat how they interact. You've got the primary control first. Think of it as the immediate reflex action.
Super fast.
Lightning fast. It keeps the local voltage and frequency stable, stops your lights flickering, prevents surges, usually works on its own. No complex chat needed.
Got it. Local stability.
Yeah.
Then there's the other end.
That's the tertiary control. It's the big picture strategist.
Ah, okay, like overall planning.
Exactly.
Yeah.
Power management for the whole microgrid, economic optimization, making sure it runs cheaply, and managing energy exchange, maybe selling power back to the main grid. More complex calculations here.
Okay, primary is the reflex, tertiary is the strategy.
Oh.
So our focus today is the middle one.
The secondary control layer.
A middle manager, you could say.
That's a good way to put it. It takes those strategic goals from the tertiary layer.
The big picture stuff.
Right. And translates them into specific instructions or references for the primary layer units.
So it ensures the power sharing is accurate, the voltage is just right across the grid.
Precisely. But here's the kicker, and what makes it so relevant for our dive.
Its reliance on communication.
It's heavy reliance on communication systems. It's constantly sending and receiving signals to do its job.
Which naturally leads to the question, how do different setups handle all that chatter?
Exactly. The paper outlines 3 main ways, 3 configurations for the secondary control.
Okay.
First up, centralized control. Pretty straightforward concept.
One brain controls everything.
Basically, yeah. A single central controller manages all the units, but that means it needs really good high bandwidth communication links to everything.
Sounds efficient for coordination.
It can be, yeah. You get good overall coordination because it has all the information, but the huge downside...
Let me guess. If that central brain fails.
The whole system can go down. It's a classic single point of failure. Plus, it can be expensive communication-wise and maybe not very flexible if you want to add new things later.
Right. Puts all your eggs in one basket. Okay, what's the opposite approach?
That would be decentralized control. Completely opposite.
So no central brain.
Nope. Each unit, each generator or battery just makes decisions on its own, using only local information.
So they're not really talking to each other.
Essentially, no communication connection between them for this control layer, the big pluses. It's simple, very reliable against single failures. If one unit fails, the others keep going. And almost zero communication stress.
But the downside must be coordination.
Lack of global information. Because they aren't coordinating, you can't always guarantee the best overall performance for the whole microgrid. It might not be the most efficient.
Okay, so centralized is coordinated but risky. Decentralized is robust but maybe suboptimal. Is there a middle ground?
There is, and that's distributed control, often seen as the sweet spot.
How does that work?
Here, the controllers do communicate, but only with their immediate neighbors.
Ah, okay. Not everyone talking to a central hub, just peer-to-peer.
Sort of, yeah, over a shared digital communication link. It's more flexible than centralized, much more resilient to single failures because there's no one central point, and the communication load is less intense.
Makes sense. How do they coordinate if they only talk to neighbors?
A key technique the paper highlights is the consensus algorithm. It's clever.
Consensus. Like reaching agreement.
Exactly. It's a way for these distributed units, through sharing data just with their neighbors, to gradually adjust what they're doing until they all converge on an optimal operating point for the group, like finding common ground without a boss telling them exactly what to do.
That sounds pretty sophisticated. So distributed seems like a good balance. But There's always a but, isn't there?
There usually is. Even with distributed control being more robust, the paper keeps coming back to one major challenge across the board.
Communication system disturbances.
Bingo. It's the Achilles heel, really. No matter the setup, if the communication links aren't reliable, you've got problems.
And these aren't just minor hiccups.
Absolutely not. The integrity, the quality of these links is paramount. Think about delays in the signals.
Like lag.
Yeah, or packet loss, where bits of information just disappear en route, or even just noise on the line. Any of these can seriously mess with the control system.
Leading to what? Instability.
Instability, oscillations in power, poor performance, potentially even cascading failures in worst-case scenarios.
Yeah.
Distributed systems have some tolerance to delays, but there are limits. Push past those limits and the system can become unstable.
Wow. So even with these smart algorithms, a shaky connection can bring things down.
It's a critical area. Improving resilience to these communication issues is a huge focus of ongoing research.
Okay. So wrapping this up, you should now have a much clearer picture of how these microgrids are controlled, especially that crucial secondary layer.
And that constant tension, that balancing act between sophisticated control and the reliability of the communication it depends on.
Getting this right is fundamental if we want to integrate more renewables like solar and wind and build a grid that's truly resilient for the future.
Which leads us to a final thought to leave you with. Given how vital yet vulnerable communication is, how can we design future microgrids? What innovations might allow them to maintain stability, to keep working effectively, even when that communication is badly degraded, or maybe even lost completely for a period?
That's a really tough question.
It is, and finding the answer will undoubtedly shape our energy future.